Hello everyone, I'm Marko.
And I'm Cameron.
Today we are going to present our work on programming and training rate-independent chemical reaction networks done in collaboration with Austin, Sarfraz and David from UT Austin. At the end of this talk, you'll gain understanding about a class of chemical reaction networks that is easy to analyze in a sequential manner despite the inherently parallel nature of chemical reactions. Moreover, we'll show how a powerful deep learning framework can be used to program this class of networks. A preliminary version of this work has appeared at ICML, and extended journal version is currently under review. And now Cameron will talk more about the computation in chemistry and this subclass of networks.
Thanks, Marco. So chemical reaction networks have found a lot of use as a programming language for the molecular computation systems that we like to build. For example, the citation here shows how you can compile an arbitrary abstract chemical reaction network into a strand displacement system that has the same dynamics and equilibria as the chemical reaction network itself. This lets us use chemical reaction networks as a programming language for our molecular computation. That's kind of the big perspective here. So we'd like to know how we can program these. One important point is the input-output convention. There are a few different input-output conventions you can use, but the one we'll talk about is the input of the computation is the initial concentrations of some subset of the species, and the output is the concentration of some subset of the species at equilibrium. So here, maybe the A and B initial values are the inputs, and the output is the eventual concentration of the molecule C. So now that that's out of the way, I'd like to talk about the special subclass that Marco alluded to, which is this class of networks called non-competitive chemical reaction networks. So a non-competitive chemical reaction network satisfies this following definition. So if some species is net decreased by a reaction, then that species should not appear as a reactant in any other reactions. So we'll see some examples. First, I'd like to show what a competitive network looks like. So this network is competitive because the species A is net decreased by both reactions here. So it does not satisfy the definition. So a non-competitive network might look like this one. Although A appears in both reactions, it is only net decreased by one reaction, and it does not appear as a reactant in the other reaction. So this network is non-competitive. This last example is nice because non-competitive networks can have catalysts in many reactions. That's the point here. So it's okay if A appears in multiple reactions as a reactant, as long as it's used catalytically in all of those reactions, and the network will still be non-competitive. So now that we understand what non-competitive chemical reaction networks are, I'd like to talk about some of the nice properties. First, I'll talk about two connected concepts, which are the easy to analyze convergence of these networks and the rate independence of the networks. So what do I mean by rate independence? So first we'll look at this non-competitive example network. I claim that it computes y equals 2/3 x. So the equilibrium concentration of y will be 2/3 of the initial concentration of x. And to understand rate independence, we can sort of decouple the part of the computation which is due to stoichiometry and the part that is due to rates. So here we'll completely ignore the rates and we'll just think about the stoichiometry. So here we can think about the stoichiometry by looking at the stoichiometry matrix. So each entry here just gives you the net increase or decrease of that species in that reaction. So for example, X is decreased by 2 in the first reaction. And using this stoichiometry matrix, we can think about from some initial state, we can think about all the states that are reachable from that initial state while obeying stoichiometry and ignoring rates. So that set of states looks like this. I'll explain in a second how we sort of fill this in and how we know what all of these states are. But first, I'd like to just point out that the horizontal axis here is the concentration of species X. The vertical axis is the concentration of species R, and the concentration of species Y is the color gradient here. So this set of states is a plane. And the initial state here is just 10 copies of X. And in order to understand how we generated this sort of set of stoichiometrically compatible states, we think of this notion of straight line reachability, which is that we take our stoichiometry matrix and we have this flux vector, which here is 2.5 comma 0, that says fire 2.5 flux through the first reaction and 0 flux through the second reaction. So it's this sort of rate independent way of firing reactions and looking at what state is the outcome. So here we have the state C, which can be reached from A. We can also sort of compose these straight line segments. So we can look at the state B, which is straight line reachable from the state C. And this lets us define this whole set of stoichiometrically reachable states. So these are the ones which are reachable by some composition of line segments. But the real reason we want to look at these line segments is because there's a theorem that we've proven about non-competitive chemical reaction networks, which suggests that, or shows that if A goes to B under this line segment reachability model, if B is a terminal state, meaning it cannot fire any more reactions, then A converges to B under mass action kinetics for any rate constants on the reactions. We can prove something a bit stronger than that also. So for any state in this set of stoichiometrically reachable states, for example, this random state A prime that I show here, we also know that A prime converges to B under mass action kinetics for any rate constants. So this captures a wide class of initial perturbations. You can start anywhere in the set of stoichiometrically reachable states. And if you let mass action kinetics take over, it will converge to the correct output state. The last thing I want to say, I can't explain, I don't have too much time to explain this, but the convergence holds for not only mass action kinetics with any rates, it holds for any fair rate law. And there's sort of a formal definition of that, but it basically captures a wide class of kinetic rate laws and probably captures your kinetic rate law of interest. I'd also like to add that an analogy of this theorem holds for the discrete stochastic model of chemical reaction networks, which says that in that model, if any sequence of reactions from an initial state can reach this terminal state B, then all sequences of reactions terminate in that state B. So it's a very strong result in that model as well. So since now that we've sort of described how these non-competitive reaction networks are rate independent and how we can analyze what the convergent state is and how easy that is just by drawing these straight line segments, I want to talk about some of the other useful features of these networks. So first, I want to say we want to take this small network and compose it into larger networks. There's a condition that's been proven in prior work about composability of these rate independent chemical reaction networks. So basically the network is composable as long as the output species does not appear as a reactant. So let's look at an example. Let's say we want to compute this function on the left here. So we're going to create these three modules using chemical reaction networks. And then we're going to compose them together to compute the entire function. So I've already shown you how to compute 2/3 of X. So we'll have two distinct chemical reaction networks for each of those. And we want to wire their outputs. So Y1 and Y2, we want to wire those into another module. So here's the module which computes them in. And this entire chemical reaction network is computes the function that's shown on the left by composing these smaller pieces. And what's nice is if each of the modules is non-competitive, then the entire network will be non-competitive as well and have all the nice properties about easy to prove convergence that I talked about before. So next I want to talk about reusability of the networks. I'll explain that, but first I need to explain what the dual rail representation is. So in the dual rail representation, we represent a value as a difference in the concentration of two species. So here we have two logical values, X and Y, and we want to compute the function Y equals minus X. And we do so just by sort of flipping the sign here. But the idea is that X is represented as the difference in concentrations between the X plus and the X minus molecule. And similarly, Y is the difference in concentrations between the Y plus and Y minus molecules. The way that this allows reusability is that imagine we initially had the system with X plus equals 6 and X minus equals 2. So the system starts converging to the output F of 4. And maybe it finishes converging, maybe it doesn't, but let's say we want to compute a different function. An easy thing we can do is we can just add 2 copies of X minus, and now we know that the system will converge to the output F of 2. So this is the sense in which it's reusable. You can just add more inputs and it will compute now the output related to those inputs. And this is due to the sort of non-competitive features that I described earlier and how easy it is to prove the convergence. Lastly, I want to talk about the computational power. So previous work has shown that the computational power of rate-independent computation is limited to continuous piecewise rational affine functions. The good news is that non-competitive networks can compute any continuous piecewise rational affine function. So non-competitive networks are sort of complete for the class of computations that they can do. So then the only question left over is sort of, is this linearity too limiting? Is this too much of a restriction on what we can compute? I think Marko has a good answer.
Yes, so I'll start by talking about the ReLU function. So what is the ReLU function? So ReLU function computes value x if x is greater or equal to 0, otherwise 0, like shown in this plot. And this function is very popular in neural network community because it's a widely used activation function. So we identify a small chemical system that computes ReLU, which is in dual rail form, as Cameron described. And furthermore, we even showed before that this is a minimal system that computes ReLU in our DNA 2020 work. So now we can actually make use of the theorem presented earlier to analyze this network. So what we can do is take the path where we first fire the first reaction until possible. So this will lead to having 0 amount of x plus. You don't have to understand all equations. But then we move to firing the second reaction till completion. And this will actually lead to the stable state. So it will leave 0 amount of x plus and 0 amount of m or x minus. And actually, if you analyze the y, the output y, it will be equal to the ReLU of the input x in dual rail form, where I skip the details of the equation. So now, logical question that we had is, can we use this ReLU to actually compose a neural network in chemistry? And the answer is actually yes. And I'll illustrate the scheme we use on this simple example. So first, I show a small neural network with 3 neurons and real valued weights. I also here show that the neuron can be decomposed into 2 operations. One is a weighted sum and other is a ReLU activation using the output of the weighted sum. So now we actually make this table where we have all individual components of neural network and we have their counterpart in chemistry. So for example, for fan out, we have this chemical system, which is simply just copies the value of input into output species, and it's non-competitive. Actually, all of the chemical reactions here are non-competitive. Then we have a weighted sum module that translates to this chemical system where if you, for example, want to compute P divided by Q, you would have a reaction with the Q molecules of X going into P molecules of Y for both positive and negative species. And then for ReLU, I already explained the chemical system. And finally, bias terms. Bias terms are the constant values that are added to the weighted sum of neurons, and they can be implemented by just setting initial concentrations of appropriate species. Now, given those nice properties of non-competitive networks, you can actually compose these modules and in that way compose a neural network. I'll now talk about one special class of neural networks that uses only binary weights, 1 and -1, and I'll say later why this is important. So this class of networks was popularized in deep learning community because of the great computational benefits, meaning that they speed up the computation and reduce the power consumption a lot. And furthermore, despite the severe restriction of the weight values, they still achieve close to state-of-the-art performance. So what this actually brings to us is that the weighted sum is simplified. At the previous slide, actually, the weighted sum can have many reactants, but in these binary weight networks, you end up with only unimolecular and bimolecular reactions, and this actually makes feasible implementation of these networks using, for example, DNA strand displacement. Furthermore, I wanted to talk about another thing, and that is that non-competitive networks are susceptible to a certain kind of optimization, and that is if you have all unimolecular reactions can be eliminated. For example, this C goes to D plus E can be removed, where all appearances of C are changed with D plus E. So what this leads is actually to very tight representation where one bimolecular reaction corresponds to one ReLU node of a neural network. Here is one illustration of the scheme. So this is a binary weight neural network. This would be a chemical implementation of it. It has 12 reactions. And also note that the size of chemical network scales linearly with the number of neurons in the neural network. And there is a reduced chemical network where you perform optimization. So here actually the size scales exactly with the number of neurons in the neural network, with a caveat that the input layer, it doesn't hold for the input layer. Okay, so what does this bring to us? Actually, it leads to a deep molecular programming where we can use our favorite deep learning techniques to use a supervised data set and train a neural network to perform well on that data set, on that task. And on the other side, we have non-competitive chemical networks, and we have the bridge between the two, that is, we can compile between the two, and thus effectively, we can program the non-competitive networks using deep learning. We do so and illustrate this on a couple of examples. One is MNest, the dataset for handwritten digit recognition. And here we train a neural network to recognize a digit based on the pixel values. And the output is the highest valued output unit is the digit recognized. We then translate to chemical network, we initialize, and we simulate. And we notice that the Y0 output of chemical network is the highest, meaning that the chemical network recognizes digit 0, and furthermore that the outputs of neural and chemical network exactly correspond to each other. Then we move to a more closely aligned applications, closely aligned data sets to the potential application of our approach. So one is a virus detection that, based on gene expression levels naturally available in biochemical environments, detects the virus present. We also show how we simulate this in chemistry, and the chemical network we simulated and see that it performs as it's supposed to be. Another exciting application is a spatial pattern formation that has important applications in tissue and organ engineering. So here we use a pattern of heart, and we have two coordinates, x1 and x2, that could potentially be implemented as chemical gradient. And then we train a neural network that, based on these coordinates, detects if the pixel on the image is black or white. We translate it to chemical network and simulate to confirm that it does the same. So we confirm, for example, for this input, that the white pixel is detected as the output is positive, and in the other that the black pixel is detected. Previously, there is a previous work in this area where authors customly designed a system for one pattern, a French flag pattern. So what our approach brings is that we can automate this, that for any pattern, we come up with a chemical system that constructs that pattern. Now, what I talked so far is mostly theoretical, and we currently are working on experiments where we want to use DNA strand displacement to implement our system. What's nice about the ReLU chemical network is that we have this compact strand displacement implementation where one ReLU requires one fuel species. So basically, first reaction is X plus fuel, they interact to produce Y plus and M, and the next reaction is X minus and M produce inactive base and Y minus species. So needless to mention that implementing the neural networks in chemistry has a long history. As far as we could track, it's from 1991. And there is a lot of experimental work, like in this Nature paper by Kevin and Luchsinger. So what is different about our approach is that it's the most compact. For a given neural network, it will produce the most compact chemical network. Then it's rate independent, meaning that one source of error that stems from tuning the rates of reactions is completely eliminated. And it's bidirectional, that we didn't talk about this, but you can also go from chemical to neural network and not just the other way around. So to conclude, we identified an easy to analyze class of chemical networks called non-competitive. We presented a neural network implementation in non-competitive networks. And we simulated chemical implementation of neural networks to showcase our approach. So the next things, actually, we are currently working on experiments. We are curious about the question of minimizing and pruning neural networks in order to get the minimal neural network and thus a small chemical system. And we are interested in exploring the question of convergence time of chemical systems. Thank you.
Thanks, everyone. We'll be happy to take your questions.